All right, so if you didn't already pick up your graded assignment, you can grab that at the end of class. Your final assignment will be collected on Thursday in class, and we're going to begin today by discussing a couple of the problems that are on there just to make sure that you've got what you need to work through it smoothly. Now the final exam is on Thursday the 15th. That's the second to last day of finals. It's after, Wednesday's a timeout for finals. And so you can spend all of Wednesday prepping to take the exam for your favorite class on Thursday and just knock my socks off, all right? That's never happened before. I've never been grading a final exam and my socks literally flew off. So I expect that that'll happen. Yeah, I want that phrase to become reality from you guys. So we're going to be in here. It's 2 hours, so that's more time than we ordinarily have for the exams. Usually we're limited to 75 minutes, right? So that gives me the opportunity to give you longer, more detailed, more confusing questions. No, that's just... the questions won't be longer or more confusing or more challenging. They'll be about the same level of difficulty as you've had on the first two exams. There will just be the opportunity for me to give you maybe 4 or 5 questions instead of the 3 that you've had so far. And I might actually break them up into smaller, more manageable chunks. Instead of one larger question, I might make it 2 smaller questions. So anyways, I'll provide the equation sheet, the same one that you saw for the midterms. Midterm exam 2 equation sheet was slightly updated from the first midterm exam. So that's still posted on MU Online if you want to get an advanced look of what the formula sheet looks like that you're going to have access to. Now, I sometimes get the question, how should you study? At the beginning of the semester, also posted on MU Online. And look through those topics and just ask yourself, which one of those topics do you feel like you could teach a short mini lesson to a classmate? Are some of them you feel that you've got down so well that you could be the instructor, or are there some of them that when you ask yourself that question, you need to review a little bit? Or, for those topics, could you write the formula that you'd use to solve problems from memory? That's another easy way to know whether or not you still have the material fresh in your mind. Is if you can still write the momentum equation, then chances are you could probably use it. But if you don't exactly know the momentum equation by heart, that may indicate that it's been so long since you solved some of those problems that you could use a refresher. Just a couple of suggestions. Whatever works well for you, stick with that. But the exam is comprehensive with an emphasis on the material covered since the second midterm. So that means there will be a disproportionate share of questions coming from Chapter 7, which we're in right now, and Chapter 8, which you'll get one class of exposure to Chapter 8. That's Thursday's class. We'll be talking about dimensional analysis and similitude. So there will be one softball question on the final exam related to dimensional analysis and similitude. So don't skip Thursday's class. Everyone gets really cheerful in here when I start talking about the final exam, so yeah, it's a great move. Well, I have a video I want to show you since we're on the subject of fluid power. It is an interesting device that they've developed and started installing in Canada. People who live in remote cabin locations, sort of like the dream situation.
Jonathan and Drew square off in the Big Easy.
We found this double shotgun style home that's over 100 years old.
There we go. how they tether the turbine to the bottom of the stream bed, I'm not sure about that, because potentially if you had a really heavy flow, it could get washed downstream. It looks pretty heavy, but another thing that I wondered about is, like bed load is the boulders that are on the stream bed, and so if you have a heavy stream flow, then those boulders will start moving, and I wonder like if they've tested those to see like what sort of a rock collision it can stand up to. But it seems really cool. I'd love to have one at my house. Free electricity, it's the dream. All right, so on the subject of hydropower, one of your problems for the assignment that's due on Thursday is this one, and it describes a similar situation, that there is some house where they have an elevated reservoir and a penstock, which is just a pipe connecting the elevated reservoir to the generator shack. And there's 34 feet of head between the two reservoirs. And yeah, this problem is in mixed units, because although the length measurements are in feet and the flow rate that's defined is in traditional units as well, they want to know the power in terms of kilowatts. So we'll have to deal with the mixed units a little bit. Obviously, since we're in Chapter 7, the energy equation is going to be a big part of this problem. So there it is. You've seen it before. But they're asking to find how many kilowatts this situation can generate if, for one thing, if there was no head loss and 100% efficiency. But then in the second, more realistic situation, they're saying of the 34 feet of head that's available, let's say that you have some allowance of maybe around 5.5 feet due to head losses. And that can account both the pipe friction and also the local losses at the inlet and through any bends that may exist. So if you allocate 5.5 feet of head to losses, and then you consider the efficiency of the two machines involved. So there is an efficiency lost with the turbine, and then another efficiency lost with the generator. And we've talked about efficiency before and how that affects the power equation. Here's the power equation, and if it's 100% efficiency, then you just use the power equation as it's written here. But what we're trying to find out is how much power can be generated here if we've got 70% efficient turbine and 90% efficient generator. In the past, when we've had efficiency factors, I've only given you one efficiency factor. You've never had to have two of them. And so when you had one, did you, in a situation like this, would you multiply by the efficiency factor or divide to find out how much power can be extracted from the system? Multiply, right, because we know that any reduction below 100% efficiency is going to give us less power that can come out. And so if you divided by 0.7, then that would mean you actually have more power coming out because of the losses. And that doesn't make any sense. And so you can always sort of reason through the situation. So when you've got two different efficiencies like this, the overall system efficiency, overall, is the product of the efficiency of the generator and the efficiency of the turbine. And so all you have to do is multiply the 0.7 and the 0.9 together. You'll find the overall system efficiency, and then that's what you use to find the power in the case of some losses and inefficiency. Easy enough, right? The losses are cumulative, in other words. Any questions about that? All right. I wanted to briefly go over problem 87 because there is some important language in the problem statement, and if you didn't read it carefully, you might feel uncertain about the losses. We've just, in the previous problem, been talking about losses, and so if you didn't pick up on some really subtle language, you may be left wondering, are there losses? Or what are they? What's the efficiency factor? And so on. So let's look at the situation. We've got a lower tank pumping water to an elevated higher tank. So we can see here's a device, it's a pump. The flow is going from left to right. They've identified the length of each pipe section and the diameter Why do you think that's provided? It's because you are going to calculate the head losses based on longer pipes have more head loss. The diameter of the pipe affects the velocity, which also has an effect on the head loss. And so since you have the pipe diameters and the flow rate is known, then you can find the velocities through each of the pipes pretty easily. But here's the important language. It says find the power supplied to the water by the pump. So they're not saying how much electrical power has to go into this motor that's driving a pump. They're saying, you know, how much power is actually going into the water from the pump. And so more power is going into the pump from the motor, and more power than that is going into the motor from the wires. But this is asking how much power is supplied to the water by the pump. And so you don't have to worry or calculate anything having to do with these efficiency factors and how much energy might be lost in the transition from wire to motor, motor to pump, and pump to water. All right? So that's the important language there. Now, they give you a formula, an empirical relationship that characterizes the head losses as a function of length, diameter, and velocity. Okay? So you've got that, and you can find out how much energy is needed to overcome the losses that are expected. And of course, it's at a different elevation, and so the pump is going to have to add at least as much head as the elevation difference between the two, and probably more to overcome the friction. And then in part B, they're asking you to draw the EGL and the HGL, and we had some practice with that in class last week, and actually several of the problems in the assignment you're turning in on Thursday ask you to draw the EGL and the HGL. So remember, some of the key points to include in a drawing like that is that for a pump, the line goes straight up. Don't draw it at an angle. It's just straight up, meaning that energy is added instantaneously at a pump. And of course, after a pump, there's a downhill slope in the direction of flow. That's because of friction losses. The EGL should end above the water surface, but the HGL should end at the water surface, at the receiving tank. And the fact that this pipe is horizontal and this pipe is inclined, that will have no effect on the slopes of the EGL and the HGL. Those slopes are only based on the velocity and the corresponding energy loss due to pipe friction. So remember that the position of the pipe doesn't affect the EGL or the HGL. The position of the pipe relative to the EGL and HGL may allow you to identify if there is any potential for cavitation, though. All right. I don't think in this last slide I mentioned this conversion factor here. I forgot to point that out. It's on the slide, but since they're giving you units of length in feet, since you've got units of length in feet, and then the unit weight of water is 62.4 pounds of force per cubic foot, in order to get watts out of the power equation, you're going to need this conversion. So a joule per second, remember, is watts, and then the flow rate component will have seconds in it. So as you look at the units in this problem, it's in your book, but it's also here on the slide that there's 1.356 joules per foot-pound of force. All right. Here's the last one I wanted to discuss with you, and that is you've got water flowing from one tank to another at a flow rate of 16 cubic feet per second. And again, we know the lengths of the pipe, the diameters, and they've even gone so far as to calculate the cross-sectional areas for you. What a nice gesture. You have to calculate what is the elevation in the left reservoir that's causing this to happen. And that elevation will only be valid at a certain instant in time because, you know, as the water is draining from the tank, the elevation is going to be getting lower and lower. So the elevation that you're calculating is at the point of time where the flow rate is 16 cubic feet per second. Now they do give another formula for energy loss due to pipe friction, and an important thing to keep in mind is that you have two pipes with different diameters. So that means the velocity is going to be different in the small pipe compared to the large pipe here. So you can't just add the two lengths together. It would be wrong if you said L equals 500 and then you picked one of the velocities to put into that formula. The head loss through the first section has to be calculated using that section's length, that section's diameter, and that section's velocity. And then you also calculate the energy loss through the second section. But that's not the only energy loss, the pipe friction. In this one, you're actually also supposed to consider two local losses. So have a look at the picture. Where do you think the two local losses are that you're meant to consider? Very good, the abrupt expansion. And the formula that you saw in class previously for head loss due to an abrupt expansion is one of the velocities minus the other squared divided by 2g. So that's the energy loss in an abrupt expansion. Where's the other one? They're saying that there's only two local losses. And so this is the expansion of the pipe is one of them. So now you've got to pick between the other two. She said the inlet, meaning the tank where the water's going from the tank into the pipe, and then the outlet. So you're saying the outlet? Yeah, and I think the reason why is that you see how they've got this taper on the drawing? You can minimize the energy loss by gradually transitioning the flow into the pipe. And even if it was an abrupt inlet, that's only 1/2 of the velocity head in comparison to all of the velocity head at the outlet. So if they're going to force us to choose on which local losses to consider, I think it's the transition and the outlet that needs to be considered. And then the energy loss at the outlet, the local loss at the outlet, is just simply V2, meaning the second pipe, squared divided by 2g. So it's all of the velocity head just vanishes. Now, of course, in reality, you wouldn't have to force between choosing which local losses to consider. You'd just include all of them, but, you know, it's a book problem, so. And then lastly, draw the grade lines. And we've already talked about some of the characteristics you have to illustrate. In this one, there's going to be a local loss at the pipe transition, and so that's a straight line down. And I showed you in my solution from the previous class that there's a straight line down at a transition like that. And then, of course, the slopes will have to be different. Which of these two pipes will have the steeper EGL slope? The first, because the velocity is faster in the first pipe. That means that the energy loss occurs at a faster rate. The EGL is going to have a steeper slope. What about the gap distance between EGL and HGL? How will they be different between pipe 1 and pipe 2? The gap distance is v squared divided by 2g, and so it's the velocity head. So what does that mean about the gap in the first pipe compared to the size of the gap in the second pipe? Which one's smaller? It gets smaller, meaning the gap in the first is bigger, right? They're further apart. The EGL and the HGL are further apart in the first pipe because the velocity is fast. So fast velocity means big velocity head. The EGL and the HGL are far apart for pipe far apart for pipe 1 and closer together for pipe 2. All right. So drawing those is a learned skill. It takes practice. Any questions before we move on? We're not in a particular rush for once. It's the end of the semester and we got where we needed to be. We're not trying to make up time, so. All right. Let's work through this one. This is a fairly complicated example that is going to give us some experience applying the energy equation with pumps. We have a tank that supplies our network, and we know the water surface elevation at the tank, and water goes into the pipe through a pump around a series of bends. We've got a couple of K values which define local losses, and then there's a building on a hill, and anytime you look around at like the rich people who live on the top of the hills, at least take comfort in the fact that they don't have good water pressure in their shower. All right? We're going to take a look in this example here. Ultimately, in part C, we're going to find out what's the water pressure at the top of the building. Because, you know, this pump is adding the energy that pressurizes the pipeline. It can only add so much. And in a city, if you add too much pressure, then the people who live at lower elevations are going to have their water heaters start to leak. That's usually the thing that leaks first, is water heaters. And so there's only sort of a narrow range of acceptable pressures. Typically, it's from about 250 kilopascals to maybe 850 kilopascals. So there's kind of a narrow elevation range that you can service with a single pump. Mm-hmm. Yeah? The regulator can't change the pressure that comes in from the street. No, I mean, you can have your own tank and your own pump, but what they usually do, like out where I live, is there's just different tanks at different elevations, and so, you know, part of the network will be serviced from one water tank that will cause a certain pressure, and then they have to lift the water from tank to tank. But if it's just a single continuous network, then the pressure would vary a lot from someone who lives on the top of the hill compared to someone who lives on the bottom of the hill. And that's something next semester in your design project that you'll have to try and optimize, is you'll have this fictional town that is on a hill, on a hillside, and you'll have to be within this range of acceptable pressures for the people who live at the bottom of the town and the people who live up at the top. Yeah.
Is it feasible to have a second pump at a different location?
Sure. Yeah, absolutely. You can have a booster pump in line. So we could have another booster pump here, and then that would raise the pressure again. Yep. Pumps in series. Okay, so let's see. All right, we've got lengths. 2 kilometers is the overall pipe length. 2 kilometers is from the tank to the outlet, but it's only 1.1 kilometers to the building. And you're going to need that different length in part C. So the first thing I'd like you to calculate is what pump head is required to get a flow rate of 580 liters per second through 2 kilometer length, 500 millimeter pipe shown below. Now there's water coming out of an outlet here. Not shown. Maybe we've got another tank that this is discharging into. Hopefully they're not just dumping it off the side of the hill. But for purposes of energy equation, let's assume that they are, all right? This is location 2 for us, and location 1 is going to be at the water surface of the tank. So calculate how much H sub P is needed to overcome the friction loss, which is defined here, and the local losses, which are all a function of the velocity head. Thankfully, the entire pipe is the same diameter, so that simplifies things a little bit. Let's double check some of these numbers. All right, so hopefully you got that the cross-sectional area is about 0.196 meters squared, and from that you can get the velocity through the pipe, 2.954 meters per second. And then if you put all of that into the formula for the head loss due to pipe friction, you get that there's 33.8 meters of head lost due to pipe friction. Now compare that to all of the local losses. If you add up all of the K values, we had one inlet loss at 1.0 and then two bends that were 0.4. So the sum of the K values is 1.8. And you multiply that by the velocity head and get that there's only 0.8 meters of loss due to the fittings, local losses. And so by comparison, you can see why they sometimes call these local losses, or they're sometimes known as minor losses. But if we rearrange the energy equation to solve for HP, because it's the only unknown when we're starting with a tank, and we know that the tank is open to the atmosphere at location 1, so there's no pressure head there. The water isn't moving at location 1, so there's no velocity head there. It does have an elevation, and the elevation is specified, 77.3 meters. And so that's the starting point. That's location 1, and then we have losses as it flows. And so rearranging the energy equation in terms of HP, which is what it's asking for, the only terms that are left is you have to have the energy that the pump is adding to overcome the elevation difference, Z2 minus Z1. And then there's still velocity head as the water comes out of the outlet pipe. And so we list the velocity head at 2 as one of the terms. The pump has to provide energy for that velocity head to be there. Then the pump also has to provide enough energy to overcome the local and the friction losses. So those are the terms that when we add it all together, that's why there needs to be 50.44 meters of head added by the pump. And you can see that I've identified each of the terms and their magnitude just so you can see, for example, that the majority of the pump head that's being added is due to pipe friction and the elevation difference. It's only a small amount of energy that the pump is adding in order to make sure that there's enough velocity head there at the outlet. Velocity head is always relatively small, and here it's only 0.44 meters of energy compared to the much larger magnitudes for the other terms, 0.8 for the local losses. Yeah?
The modified energy equation, how exactly do the local losses and friction losses come into play just from that energy equation?
What's the modified energy equation?
Well, I mean, you went from HL to H sub 0 plus H.
Ah, right. Okay. Good question. So here in the energy equation where it says HL, that means head loss is the sum of two terms. It's the friction losses and the local losses. And so we calculated both of those separately in this problem and then combined the two in for this term H sub L. Are there other questions? No? All right, so part B of this is asking, assuming that the motor / pump is 58% efficient, what's the electrical power required? All right, so the power equation, you've seen it several times already today, but it is the power is the flow rate times the unit weight times the pump head. And then since we're talking about electrical power required, think about it rationally. We know a certain amount of power has to go into the water, but how much electricity has to go into the motor / pump in order to make that power go into the water? It's got to be more because of the losses. And so that means, in our case, we're going to be dividing by the efficiency factor to make the electrical requirements higher than the amount of power that actually goes into the water. Okay, so part B. All right, so you have to divide by the efficiency factor because the first thing that we did in Part A was we found out the amount of pump head that the system requires. And so you can't base your power requirements just based on only the pump head, because there are going to be losses inside of the motor and the pump. And so you have to put more energy in to the motor slash pump than you're going to get out of the motor slash pump. So we add 494 kilowatts. Sorry that's cut off. It was A4 size paper and it scanned it in letter mode, so it sort of chopped off the top and the bottom a little bit. But it's 494 kilowatts. All right. Now the last part, what is the water pressure at the top of the building? So here is the penthouse suite on the top of that fancy building there. Really looks like someplace I'd love to live. No windows or nothing. All right, 102.69 meters is the elevation of the top of the building there. So we want to find out what is the pressure. Now, the head losses are going to be different than what we calculated in Part A, because the length is only part of the way through the system. So you're not going to use 2 kilometers for calculating the head losses. You'll use the distance of 1.1 kilometers. And then the elevation, the Z2, will be different than it was in the first part. Finally, one other thing is assume that in the, at the top of the building, what we're calculating is the static pressure, meaning the pressure in the faucet before you actually turn it on and the water begins to flow. So what that means is let the velocity of the water at location 2 be equal to 0. So here's 1 at the tank, 2 is at the top of the building, and the water velocity is 0 under static conditions. And that's what we want to know, is the static pressure. Yeah, that's right.
I didn't account for it.
All right, so we have to calculate a new friction loss, because we're only interested in how much energy is lost between the beginning tank and the building. So that's 1.1 kilometers of pipe instead of the full 2. Now the local losses are the same because all of those local losses were before the building. So that remains 0.8 meters of local losses. And the pump head's the same too, because the rest of the pipe network is still there, so the pump has to add as much energy as it always was. It's just we're looking at a different spot in the network. And so the fact that we're looking in a different location doesn't change how much energy the pump is required to add to make the system do the flow rate of 0.58 that we're looking for. So the pump head's the same. So here is the energy equation solving for the pressure at 2. And when you make all the substitutions, the pump head is 50.44 meters of energy. That's like what we're looking at here is what caused the pressure at 2. The pressure at 2, some of the energy that exists as pressure at 2 is because of the pump. 50 meters of that pressure head is due to the pump. Some of it is due to the elevation difference, but actually it's a negative elevation difference. So if anything, the elevation difference is reducing the amount of pressure that otherwise would be there due to what the pump is doing. And the same is true of the friction loss and the local losses. So the only thing that's contributing to positive pressure at location 2 is the pump, but it's not giving very much pressure. That 56 kilopascals is below what's considered safe. Even in an emergency, water networks are supposed to maintain at least 140 kilopascals of pressure in order to keep something called backflow from coming into the system. What you don't want is you don't want someone to turn on their faucet and have the system start sucking air in. That's the situation that's known as backflow. And the reason why that's dangerous is that then you can have contamination in the water network. Imagine flushing your toilet and the water goes the other way. That's not what you want, right? You want it to go down the drain and not back into the water pipe. So they set as a relative guideline that even during like a fire, and that's when pipe networks are taxed the most, is when there's a fire and the fire department is using really a lot of water out of the network, the pressures will drop. But about 140 kilopascals should be maintained. And here we've only got 56. And so those rich people on the penthouse suite probably, they're hating life. They can just get drops of water out of the shower head. Unless they put in a booster pump. But
What happens to a pipe making work inside the house during the fire? Does it just become open atmosphere?
are we talking about a fire is in the house? So your house is on fire. What happens to the pipe network? That's your question?
Yeah. Energy go into it?
Because of the fire?
Yeah.
All right, so the flames heat up the water. I guess the water could start to boil. All right, so that's cavitation, so it's going to begin expanding. I guess the pipes could burst, and if you're lucky, they'll burst in such a way that the spray pattern puts out the fire. And then it's freezing out, so then the water freezes around it, and then it seals up the burst pipe, and you come home none the wiser. Yeah.
Hey, why is everything all wet?
All right, guys. So I'll see you on Thursday with that last assignment. And then a week after that, we'll have our final party of the semester, the final exam. All right. Have a good day.